The next topic is about the damping system. The deflection torque produces the deflection. The deflection torque produces deflection. To control that deflection, the controlling torque acts in the opposite direction to control that deflection. So after that, to the pointer. So before coming to the rest, the pointer will move to and fro. It is known as due to inertia. Inertia means, if for example, if we see, if we take bus as example, when we traveling in bus, if driver suddenly applies the brake, we all fall forward. Why? Because we can't control our body movement suddenly, so that's why we fall forward. So if we take another example, fan as example, while we switch off the fan, it will take some time to stop the total rotating. Why? Means it is because of inertia. It moves for some time and comes to the rest position. So it is called inertia. Unless the pointer rests, we can't get the final value. ఆ పాయింటర్ అనేది రెస్ట్లోకి వస్తేనే కానీ మనకి ఫైనల్ వాల్యూ ఏంటిది అనేది ఇక్కడ తెలియదు. సో ఆ to bring that pointer to the rest position, we use the damping system. In this instrument. So it is called the damping torque. This damping system provides the damping torque. So this damping torque is directly proportional to velocity, and this damping torque does not depend on the current. So if we see in this figure, in this graph, so in this graph is critically damped. This is over damped. These oscillations are under damped. So if we take the critically damped system, if we see the critically damped, the graph, the moving system, if the moving system reaches its final value smoothly, it is known as the critically damped, and it reaches soon, so it is the critically damped. If the regarding over damped, in this over damped system, if it moves slowly to its final position, it is known as the over damped system. So regarding this under damped, it will oscillate. In this, the moving system will oscillate to its final position and final steady state with decreasing amplitude. This is known as the decreasing amplitude, and it reaches the steady state. This is known as the under damped. So all these critically damped, over damped and under damped, all these are regarding the instrument. So whenever in instrument the moving system reaches to its final position in smooth manner, it is known as critically damped. If the moving system slowly reaches to its position, steady state, final position, it is over damped. In instrument, if the moving system oscillates with decreasing amplitude, it is known as the under damped. So this is regarding in instrument. So to we use 3 methods. Those 3 methods are air friction damping, fluid friction damping, eddy current damping. These 3 are used to produce the damping torque. So first if we see about the air friction damping, this is the picture of the air friction damping. It is this air friction damping is used when deflection torque doesn't have strong field. When it doesn't have strong field, we use the air friction damping. So in this is the pointer, this is the scale, and this is the air chamber. This is piston. This piston is made of light weighted aluminum piston. This is a spindle. Spindle means which holds the pointer is known as the spindle. So what happens in air friction damping is when the piston moves in the fixed air chamber. This piston is moved in the air chamber. The clearance between the piston and chambers is uniform and small space. If we see for air chamber and piston, there is no space. A small space is, we are having small space. So when the piston reciprocates to the chamber, when there is oscillations, the piston will reciprocates. Reciprocating means reciprocating means it will move forward and backward. Movement of the piston is known as the reciprocating. Inside the chamber, whenever there is oscillations, the piston will reciprocate forward and backward and forward. It is known as the reciprocating. So when the piston moves in the chamber, the air inside the chamber will compress and the pressure of air is developed due to the friction. When the piston is moving forward and backward, there is a compression and pressure is developed in the air. Due to this pressure and compression, the friction will opposes the motion of the pointer. Due to this compression, whenever the piston moves up and down, there is a compression there is a compression and pressure in air. Due to this pressure and compression, there will be a friction developed in the air. There is a friction developed in the air. So due to that friction, it will try to stop the motion of the pointer. That means it will try to stop the oscillations of the pointer in this air friction damping. So when it opposes the motion of the pointer to not move, there the oscillations will slowly reduced. So this is reduced due to the to and fro of the piston. When it move upward and backward. To and fro means moving up and down. It is known as the to and fro. So due to this up and down movement of the piston, there is a compression and pressure developed in the air, and this pressure, there is a friction in the there is friction developed in the air, and due to that friction, it will reduce the movement of the pointer. So due to that the oscillations will come to slowly reduced due to this piston movement. So this is about the air friction damping. So this is the procedure that happened in the air friction damping. So the next damping method is the fluid friction damping. This fluid friction damping is used when the efficient damping is required. When the efficient damping is required, we will use the fluid friction damping. The procedure of the principle that works in fluid friction damping is similar to that of the air friction damping. So in air friction damping, we use air. Here we use the oil, damping oil. This is the damping oil. This is the spindle. And this is the vane or disc. So what will happen in fluid friction means when the friction between the disc and the fluid is used for the opposing motion, the damping force due to the fluid is greater and there is due to the viscosity. So this disc is known as the vane. The arrangement is like this, and it consists of the vane and the spindle is completely dipped in the this vane is completely dipped into the oil, and due to that movement the frictional force is developed and the vane is used to produce the damping torque. So whenever there is a rotation of the disc, the oil means it is a viscosity. It is viscous in nature. So due to the viscosity, the damping torque is produced. So it opposes the oscillating behavior of the pointer. This viscosity produces the damping torque, and it will oppose the oscillating of the pointer. So likewise we can reduce the oscillations of the pointer by using fluid friction. So this is about the fluid friction. Next, the last damping is eddy current damping. It is used for when efficient damping is required. So mostly in almost all instruments we use this eddy current damping, most effective in providing damping. Why we use means it is most effective in providing damping. So based on the Faraday's laws and Lenz's law, what is Faraday's laws means when conductor is placed in varying magnetic field, the EMF is induced. It is known as the Faraday's law. We all see this Faraday's law and Lenz's law in EMF as well as electrical machines. So what is Faraday's law means when conductor is placed in varying magnetic field and EMF is induced inside the conductor. So regarding Lenz's law, the direction of the current induced in a conductor by a changing magnetic field, it is known as the Lenz's law. So the disc in eddy current damping, so in eddy current damping we use the aluminum disc. This aluminum disc is connected to the spindle. Why aluminum disc we use? So why we use aluminum? Why can't we use steel or other material means? So this aluminum material is a non-magnetic material. It is non-magnetic material. And next one is this aluminum material is cheap and easily available. And third thing is the surface of the aluminum oxidizes quickly for invisible barrier for the corrosion. Corrosion won't take place that much easily because aluminum material on the surface it oxidizes quickly. So that's why, and it is light in weight. It is so light. So that's why we use the aluminum. So we use these aluminum conductors in transmission systems, in power systems also. By means it is light in weight and cheap and less cost. Due to the less cost we use the aluminum material. So for pointers also, in measurements for pointers also we use the aluminum material only. So when the pointer oscillates, this aluminum disc produces the magnetic field of damping magnet, rotates under the magnetic field of damping magnet. So what happens, so see this eddy current damping figure. This is the figure of the eddy current damping. This is the spring and it is mounted with the screws. This is the pointer and this is the aluminum disc. This is spindle. Spindle means which is a holding of the pointer, which holds the pointer in a straight path. It is a straight standing path. It is known as the spindle, and this is the damping magnet. This is the damping magnet. So this disc cuts the flux which causes the induced EMF. This induced EMF circulates the current inside current through the disc. So these circulating currents are known as the eddy currents. So the direction these circulating currents are called eddy current. Causes relative motion between the disc and field, which causes these circulating currents, which causes the relative motion in the disc and field. So due to this opposing torque, the pointer will stop oscillating due to the damping torque whenever the damping torque is produced. So to bring the pointer to rest quickly, this method is most effective method is this eddy current damping. In starting I told this is mostly used in all the instruments. So this is this is about the eddy current damping. Eddy current damping, I would like to share some more points regarding the regarding important points. Deflecting torque is greater than controlling torque. It is in underdamped. Deflecting torque is equal to controlling torque. It is in critically damped. Deflecting torque is less than TC. It is over damped. So in which instruments we use the air friction damping is PMMC, permanent magnetic moving coil. In fluidic friction damping is used in MI instrument, moving iron instrument. Eddy current damping is used in vertically mounted instruments. Electromagnetic damping is used in galvanometer. So here galvanometer means it is a special ballistic galvanometer having small control torque. It have the small control torque and high electromagnetic damping. It is a ballistic galvanometer having small control torque TC. And it measures small amount of current. Small electrical current. So the next one is instruments. In instruments we have two effects. One is magnetic effect and another one is electrostatic effect. In magnetic effect, this magnetic effect is present in moving coil and moving iron. So the instrument which comes under moving coil is permanent magnet moving coil and electromagnet moving coil. For this permanent PMMC, deflecting torque is BANI, and for EMMC, deflecting torque is I square dm by d theta. So these are important. And in moving iron we have two types, attraction type and repulsion type. For these two, the deflecting torque is half I square dl by d theta, and in electrostatic effect is present in electrostatic voltmeters, which measures the voltage, and for this deflecting torque is half v square dc by d theta. Here moving iron means we measure current. Measures current, that why here TD we have I square. Here electrostatic voltmeter TD it measures voltage, that's why here we have half v square dc by d theta. So next one is gravity control and spring control. For gravity control, controlling torque is K sin theta. It is sin theta. K sin theta. For spring control, controlling torque is equal to k theta. That means ks theta, this is kc theta. In equilibrium state, in both gravity control and spring control, we have deflecting torque is equal to controlling torque. Both are same. Here in gravity control, deflecting torque is directly proportional to current, whereas in spring control also deflecting torque is directly proportional to current. In this gravity control, current is directly proportional to sin theta. In this, current is directly proportional to theta. So here gravity control, it is a uniform. It is so in this it is the uniform, it is non-uniform, this is uniform. Non-uniform means these lines are not in scale, these lines are not in uniform way. In this, the lines are in scale, we have the uniform lines. So this is about the measuring instruments. సో ఈ వీడియో కానీ మీకు నచ్చినట్లయితే లైక్, షేర్, సబ్స్క్రైబ్ టు మై ఛానల్. థ్యాంక్ యూ సో మచ్ ఫర్ వాచింగ్.